Introduction to Algebra, we are going to be talking about Chapter 7, Proportion. 7.1 is called direct proportion. Direct proportion is when two variables directly correlate to each other, like these two squares, whereas if one square gets bigger, the other also. 7.2, inverse proportion. This is when things get weird. When one variable gets bigger, the other one gets smaller. 7.3, joint proportion. In joint proportion, we use direct proportion and inverse proportion interchangeably together, such as 1 is directly proportional to 2 and 1 is inversely proportional to 1, such as these dog relating to the sun and a ball. After that, there is 7.4, rate problems. This is where we use all our knowledge and put them together to finally use real-life problems to try to test our knowledge. Most commonly, they are used for like speed and anything that is measurable. These word problems can have a lot of technical difficulties, and it is mostly related to logic and number sense, which put those reading skills to the test. After that, we'll have a review, which will test your knowledge and make sure you have learned everything properly and correctly. There will be one question that will be randomly picked from one of the 4 lessons, preferably the last one, because it incorporates word problems on already the foundation basis of the first 3. Then we would have a challenge problem, which personally I would dislike because it makes you think a lot. However, it does higher your skill, makes you develop new skills that you can't really learn from a book. It's more like from experience kind of stuff. So on to the first lesson, 7.1. Please bear with me that I used the wrong coloration. So it's going to be direct proportion. So really talking into the scope of direct proportion, it is about direct correlation. So this is the one that is going to be mostly used in real life, the one with most real life examples. So how does this really correlate with your real life examples? Well, for real life, there's many things that directly correlate, such as you can say food. If there's more people, there's going to be higher prices of food because essentially you have to buy more food. Or you can talk about art supplies. The bigger of a drawing you will draw, the essentially bigger and more expensive of art supplies you're going to need for that art project. So how is it put into an equation? X divided by y equals k, whereas k is a constant, or x equals ky. So what is x and y? X and y are essentially placeholders for numbers that you are going to use later on. And then k, the constant, is commonly referred to as the ratio of proportionality, or the constant of proportionality. So we are going to more commonly refer to it as constant of proportionality in my preference, but both are used interchangeably in most books, I'm sure. So how does this really put into sense? How would it make sense? Let's put this car into perspective. So the bigger car and the smaller car, there's going to be a constant that changes them. And then now we have a water bottle. This water bottle is big on the big car and small on the small car. That is because they relate directly. So if you have a shrink rater, you shrink the big car, the bottle will essentially shrink with it. Now let's put all of that into the test. Question about Robin. Robin would be equal to R, and Robin is essentially a very good daredevil. He decides to climb a flag, and to see if he could do that, he climbed this 40-foot flag. While a friend of his, who was only 4 foot, looked down, he asked, "Hey, Robin, how long do you think your shadow is if my shadow is only 0.8 feet?" So Robin is essentially on the flagpole, and his friend is on the ground. His friend is only 4 feet. The flagpole is 40 feet. Robin is 6 feet. The shadow of the friend is 0.8 feet, and the friend asks Robin, "How long do you think your shadow is?" So we're going to put that question mark for the shadow as X. So what do you think it would be? Okay, so what I'm thinking is we start with ratio and proportion. We know ratio is, well, basically proportion. So let's put that to the test. 4, which is height of the little, and R plus 40, which is the height of the flagpole and Robin, which is equal to 0.8 divided by X, which is both of their shadows. And you continue solving that by R equals 6, which we already know because we know Robin is 6 foot. You continue solving to get at 9.2. So if you were wondering how we got from the essentially second step to the third step, that was by cross multiplication or butterfly. Moving on to the next one would be inverse proportion. Again, the coloration is off, so if you're a perfectionist, I'm sorry, but best I could do. So in inverse proportion, it is basically inverse. We talked about X and Y being direct, so inverse is basically the complete opposite. Let's put it in an example. Let's say X and Y are inversely proportional. So how would that make sense? Instead of X divided by Y is constant, it will be X multiplied by Y is constant. Which makes the equation X times Y equals K, which is constant. So in real life, this isn't as applied as much, except for some variations for such as eating with friends. Like an example would be if you ate at a rate of X and you wanted to eat this pizza with Y number of friends, how long would it take you? This one, rate, is indefinitely involved more than it is used in direct proportion, and number sense really comes in clutch. So here we have a problem. Pretend we have 5 friends who want to mow a lawn. They mow at the rate of 12 hours per lawn. So how much people would it take to mow the lawn in 3 hours? So again, the question would be, if 5 friends can mow a lawn in 12 hours, how many people would it take to mow the same lawn in 3 hours? Okay, let's start. So first we know that 5 people mow a lawn in 12 hours. So one person would mow a lawn in 60 hours, we do that by mowing along is essentially an equal sign. So basically, if one side we divide on 5, the other side we must multiply by 5. So the rate of one person is a 60th of the lawn per hour, which essentially equals 60 people can mow the lawn in 1 hour. By the same way, then 20 people can mow in 3 hours. And that's basically it. So how that makes sense is you basically have to use it same way as the equation. However, the special circumstances it is, you can't really put it into perspective of an equation. These are especially hard for me, so if you're having trouble a lot, when I was doing it, it is just more of a experience. It is mostly using logic and number sense, so basically the more problems you do, the more comfortable you will get with them. The next one is joint proportion. This one for me was not fun. It was mostly word problems, which doesn't make it any better. In real life, this is applied in the least, I would say. AOPS had referred to the idle gas law. I have never really gotten it, but if you want to search it up, it is PV equal nRT. So let's put it into perspective and into this example. Let's say variable x is jointly proportional. So then x is directly proportional to 2 or more variables. Now, most commonly it would be 2 variables, but there are exceptions that I have not seen yet, but it is definitely a possibility. So put that into an equation that would be x equals kyz. Again, k is the constant. So into an equation, normally we see that when we try to solve for the constant, it will be x divided by y multiplied z. There isn't much to say, so we're going to start with the problem to see if we could get a feel for this problem. So this would be 5 chickens eat 10 bags of feed in 20 days. How long does it take for 18 chickens to eat 100 bags of feed? So we have realized in the first sentence of they gave us, there was 3 numbers. Essentially, that means it's jointly proportional because inverse and direct proportion, there is only 2 variables or placeholders. So first we identify the variables and numbers, and then we realize which ones are the variables, which ones are the placeholders, essentially. So we realize that the chickens and bags of feed increase together. That means they are directly proportional. And as I have said before, there's only 2 that could be directly proportional to each other. So from that conclusion, of the same way, for the number of days, we realize chickens and the number of days divided by feed is the correct way to put this. Now, we replace the placeholders with the actual numbers, and then we get 10. So 10 will be our constant, essentially k. Next, I shall abbreviate because I did not plan space very well. So I ran out of space. C is chickens, T is time, F is feed. We plug in the two numbers we do know, and we just leave time as it is. So we moved 10 down to put it as an equation, so we only have one variable which we could solve for. And if you have solved correctly, should be 55 and 5/9 days, essentially 56. Next we move on the troubling rate problems. This is where we put everything together. This is like fitting puzzle pieces. It was extremely hard for me because it was word problems. It was word problem after word problem. So here's some things to look out for. Firstly, it's mostly about travel, like car distance, how fast people run, how fast you move, accelerators, airplanes, that kind of stuff. So it is important to know the speed formula, which is speed equals distance divided by time. You could also use it for distance and time by manipulating the equation around. It's just basically anything measurable. The things to look out for are keeping careful track of units. There's going to be a lot of changing units, a lot of units you would have to change, and a lot of units that you'll have to change back. So if you lose track, it is very easy to get the wrong number because of a forgotten unit change. Next are problems involving moving objects. That's basically every single problem. But the most I'm applying them to are the ones that actually have speed. They've given you the speed, the rate they're moving at. So consider them instead of as a single, consider them as in relation to each other. That would make your two speeds into one speed by using distance or addition, subtraction or addition. So as I mentioned before, I said rate time and then distance. For those who are confused, rate time is basically distance. In the book AOPS, they will use them interchangeably, and it's a good thing to consider when they say rate time. Oh, it is distance, and I could put it into the distance formula. And lastly, a good diagram. I didn't realize this in the first half of writing this, and it was very challenging to try to visualize something from words. So when I slowly put that together and piece up the words and have a complete diagram from this chapter of a paragraph, then it's much more easier for me to understand. So now we're going to have one about Bart and Bob. Bart wants to fill up the whole blackboard with chalk, and then Bob wants to erase it. So how long would it take Bart to write on the whole blackboard if Bart can write faster than Bart can erase? So we know Bart will write the whole blackboard in 50 minutes. So Bart will write 50th per minute. Erase the whole blackboard in 80 minutes, which means Bob will erase 80th per minute. To put that into an equation, we will get 50th minus 80th, which is Bart minus Bob, equals 3/400. And then we will give time a letter, which is t, and then put that into an equation. Solving that equation will get you 133 third minutes. Okay, and then lastly we have review and challenge problems. The review problem would be that there is a scientist who tagged 50 fish in this lake. When he caught 75 fish, there was only 3 tags. how many fish are there in total in the lake? First, we set up an equation with ratios and proportion, which is 3 divided by 75 equals 50 divided by x, which we set up as for total fish. Using butterfly or cross multiplication, you will get 3x equals 50 times 75. Solving that could give you 1,250 fish total in this lake. This is only pretending that the fish you caught were accurate representation / ratio for the fish total. For the second one, they ask you, how long would it take for the population in the human world to increase by 1 billion? They give us that there's 4.2 births per second and 1.7 deaths per second. As we talked about in rate problems, we will put them together by minusing them, which we get 2.5 increase of people per second. Excuse me for my unrated spelling, but it said rate problem. So yes, this is essentially a rate problem from the rate problem lessons in 7.4. Using that, we could use the speed formula, which replacing s with r, we would get rate times time equals amount, which means time equals amount divided by rate. So 1 billion divided by 2.5 people per second would essentially take that much people. Well, that's a lot of seconds that I don't want to say because it's so awfully long. We are going to convert it into years, which is awfully much better. And using conversion factors, 1 minute equals 60 seconds, an hour equals 60 minutes, a day is 24 hours, and a year is 365 days. We could essentially cancel out all the variables except for year. Now, solving that with a calculator or not, you're going to get around 12.7 years. So that's how long it would take. Thank you. Bye-bye.